Hello students. So in this class we will continue with the numericals on Smith chart. So problem statement is determine the input impedance of a 200 ohm line and 3 by 8 wavelength long terminated in 100 ohm resistance using Smith chart, and also find reflection coefficient, that is gamma, right? The problem statement is to determine what input impedance, that is ZS, we need to find, but what they have given is L by lambda wavelength values they have given, that is 3 by 8, means 3 by 8 is what L by lambda value, and as well as they have given load impedance long terminated in a 100 ohm resistance, means ZL is what 100 ohm. Then here they have given characteristic impedance of 200 ohm, that is Z0, right? The first and foremost step in the numericals of Smith chart is what? Normalization, doing the normalization of the resistance values. So small ZL will be capital ZL by Z0. So capital ZL is how much? Load impedance, it is 100 ohm. Characteristic impedance is what? 200 ohm. So ZL by Z0 results in 0.5 plus J 0. Here reactance part is what? 0. Where a constant resistance part, pure resistance part is what? 0.5. Right. So this impedance has to be plotted on the Smith chart. Right. So as shown in figure, we will see how. See, 0.5 will appear here. So for more clear information, here you can see here. So it is a 0.1, 0.6 here, 0.5 is here. So this is our load point, that is ZL, normalized impedance, that is ZL. With this distance of O and A as a radius, you should draw the circle now. We will see here. See, this is the O, center, A. Here it is a 0.5. With O as radius, we should draw a circle like this. This is called constant rho circle. See here, this is what? Constant rho circle. This is the point A is what? Load point. Point A is what? Load point. Its equivalent wavelength L by lambda value is at this point, that is point B. So now we will see the solution, what exactly the next step is. See here, yes, circle we have drawn, OA as a radius, that is fine. Next they have given L by lambda value, that was 3 by 8 equal to 0.375. Means from a load point this much of distance, from load point from this much of distance, we have the source, that is the generator. There we will get the input impedance. See here, a distance equal to L by lambda, that is 0.375, is moved from point B on a periphery of the Smith chart clockwise direction to get B dash. See, from this diagram we can easily understand, assuming that here it is a load end, that is a load point, that is A, right? From load point this much of distance, that is L equal to 0.375, right? So there we will get the point A dash, that is what? Input impedance or source impedance or generator impedance, right? So from this load we should move to the generator. So but this is what the just pictorial representation, but how to get in the Smith chart, that is very important, right? So in the Smith chart, see here, this is our load point. So corresponding wavelengths are at the periphery of the Smith chart. From this load point we need to move 0.375 distance clockwise direction, that is towards wavelength, towards generator. You can observe here. See here, from this point, see 0.5 is our load point. From this point, see here, you can observe here, it's a wavelength towards generator. How much wavelength we need to move to the generator, that is very important, right? Now you see here, this is our load point. See here, from here 0.375 distance we need to move in a clockwise direction. See here, 0.375 distance, it starts from 0 here, 0. So you know, if you traverse a complete one Smith chart, one circle, this results in 0.5. Half of the Smith chart will be what? 0.25. Means our 0.375 lies somewhere in between this 0.5 and 0.25. See, that value is appearing here, that is 0.375. We'll call that point as B dash. So here it is more clear, we'll see. See here, it's a 0.36, 0.37, 0.38, exactly middle you will get that point. So from a center O, we should draw a straight line which cuts the rho circle. You see here, O as the center, this B dash as a point, right? Just draw a straight line which cuts this constant rho circle at the point A dash, and then periphery at B dash, right? What we have done is what? Just we have moved 0.375 distance from what load point towards the generator. There I will get the input impedance, that is ZS, right? So now we got B dash point as well as A dash point. Now this point is what? Our input point, right? So how to get these values? We need to check. See, at this point it cuts constant resistance circle as well, constant rho circle also, right? So this is what value having, say this is corresponding value you need to see here, it is 0.8, and then corresponding arc value here is what? 0.6. Similarly we need to see here exactly. See, once you get that arc and constant resistance circle values, we need to write here in this way. So ZS will be 0.8 minus J 0.65 minus sign because it is lower half of the Smith chart, right? While entering into the Smith chart, we will make it normalization, right? So but in the case of while taking back the values from Smith chart, we need to multiply the Z0, that is characteristic impedance. 0.8 minus J 0.6 into 200, so that results in what? 160 minus J 120 ohm. So this is what the required source impedance for the given, right, numerical, right? The last point in the numerical is what? To find the voltage reflection coefficient. How to get that voltage reflection coefficient? With OA as the radius, we know that with OA as radius, so just cut the readings at the reflection coefficient line, so there you will get the magnitude, and then what is the angle reflection coefficient, so that we need to write here how much it is. See here, it is 0.33 magnitude, we are getting 180 degree, that is phase angle at point B. This is the phase angle at point B. Here you will get the 180 degree. This is the solution for the given numerical. Okay, we'll move on to the next numerical. So that is a 300 ohm line is terminated by an unknown impedance. A VSWR is 4.48 and the first voltage minimum is situated at 6 cm from the termination and the frequency is 200 MHz. Determine the unknown load impedance if the line is in air. A phase velocity is equal to velocity of light. So this is what the data given. We need to find unknown impedance, that is load impedance. In the previous numerical we have identified source impedance, that is ZS, right? Now our task is to find what? ZL. What all they have given? So 300 ohm line, that is Z0 characteristic impedance they have given. Standing wave ratio rho value they have given, it's a 4.48, right? As well as dV minimum where it occurs, voltage distance at which V minimum occurs, so they have given, that is 6 cm. That is the first D minimum, right? First and foremost step is what? Draw a row circle with a 4.48. See from O as a center, just you see here 4.48 where they will get, means that is a row with that much of radius. You draw a constant row circle which shows that rho is equal to 4.48. So can you observe here, this is the constant row circle. We know that this right hand point where it cuts horizontal axis this circle, this is what V max, right? Point D is V max, point E is what? V minimum, right? You can observe here one diagram. See, this is a load point, these are the reflections. This is the first V minimum, second V minimum, but what they have given, first dV minimum distance from the load they have given, that is 6 centimeter dV minimum, right? But we cannot enter the dV minimum value directly, but all the values on the Smith chart are per wavelength. So therefore dV minimum by lambda we need to enter into the Smith chart to get load impedance. For that reason we need to find lambda. So how to get the lambda? Lambda will be what? C by F. C is what? Velocity of light. It's a 3 into 10 raised to 8. What is F? They have given F value frequency, that is 200 megahertz. Substitute the values of that. So lambda equal to C by F, we will get 1.5 meter or else 150 centimeter, right? But this is what the lambda value, but we need to get the dV minimum by lambda ratio. So therefore 6 centimeter by 150 centimeter, this results in 0.04. The meaning of this 0.04 is from V minimum point, means this is our V minimum point. From V minimum point, if I move 0.04 distance on the Smith chart towards load, wavelength towards load, there I will get what? ZL. So that's what the procedure now. Now see here, from point E, so this will be 0. I should move 0.0, how much it is? 0.04 distance. See, from this point I need to move wavelength towards load 0.04 distance. It's more clear here. See here, from this distance 0, I need to move wavelength towards what? Load here, second most outermost circle. 0 here, it's a 0.04 here is there. We can observe here 0.04, 0.05. This is the point. From this point we need to draw a straight line towards what? Center of the Smith chart. That's what they have done here. From that 0.04 distance, this is the center which should cut what? Constant row circle. This distance is called as dV minimum by lambda, which is equal to 0.04, right? See, it cuts at this constant row circle, corresponding constant resistance circle value as well as arc value we need to see, not this point where exactly it cuts the circle. At that point we have the arcs as well as resistance points. For this resistance value are 0.24 as well as 0.24 arc also. Minus sign is because it is lower half of the Smith chart, right? This is what the small ZL, but we want the capital ZL value. So capital ZL equal to small ZL into Z0, where Z0 is a characteristic impedance. So that's what they have given, 300 ohm. See, 300 ohm. So therefore if I multiply that value 300 ohm, so we'll get ZL as 72 minus J 72 ohm. This is the load impedance. I'll just summarize the today's numerical. Here I have solved two kind of numerical. So in the first numerical, they will give L by lambda value. That's what? See here, L by lambda value. So I need to move this much of distance towards the generator from load point. In this numerical, they will give the load point, that is ZL. If I move this much of distance towards the generator, that is clockwise direction on the periphery of the Smith chart, so there I will get what? ZS. See, this is the load point. If I move clockwise direction of L by lambda distance, whatever it may be, here in this numerical it's a 0.375, there I will get what? ZS. Where it cuts the row circle, there we should find constant resistance value as well as arc value. If that arc value is below the Smith chart, So means below half of the Smith chart we need to take minus sign, and then we will get some values. We should multiply the Z0 for that to get ZS. Right, this is the case of to find ZS. In the second case, what they are given is rho circle is given, that is 4.48, as well as Z0 is given, and dV minimum is given, means the first voltage minimum from the load point they are given. So for that we need to find lambda also. I identified lambda is by C by a formula, and then dV minimum by lambda also. Now if I got this point, meaning of that one will be, listen, this is very important. From this dV minimum point, if I move dV minimum by lambda distance towards load, there I will get the ZL. But how to move in the Smith chart? So from dV minimum point, this is the dV minimum point. So if I move dV minimum by lambda, that is 0.04, wavelength towards load I should move, not wavelength towards generator. I want to find load point, that is load impedance. Therefore if I move dV minimum by lambda, that is 0.04 towards the load, there I will get what? Load point. See, draw the straight line from that point towards the center of the Smith chart. It cuts the rho circle at this point, say point X or point F, right? So here we need to find corresponding resistant value as well as what? Arc value. Since it is lower half of the Smith chart, take a value which is arc value as a negative, then you will get some values, say 0.24 minus 0.24. So this is not the final answer, this is the normalized value, right? We want the actual values, so we need to multiply Z0. It's very simple value. Entering into a Smith chart, impedance should be normalized by dividing Z0. While taking back out from the Smith chart, we should multiply the Z0. It's very simple. So if I multiply characteristic impedance 300, so ZL I'll get what? 72 minus J72. So probable kind of questions. So they may ask like a reflection coefficient, ZS, ZL. I covered three kind of numericals. So in the next class, we'll discuss the impedance matching concept. Okay, so that requires some basics, and more complex things are there. We'll solve one numerical on that. So we'll stop it here. Thank you.